Hi everyone, I'm Manasi Wijerathna from GHD, Sydney, Australia. The paper I'm presenting today is Impact of New Tunnels on the Performance of Existing Tunnel and Tunnel Liners. This is a study based in Sydney region. First, the overview of my presentation today. First of all, I will talk a little bit of background, as in why did we need this study. Then the bit more explanation about the utility tunnel. That was the objective of our study. Then the finite element modeling, analysis results, and finally the conclusions. To start with the background, as we all know, the ground surface in most of the city areas nowadays are densely populated with existing structures. So there is no more space there to do new developments such as infrastructure projects or other services. Therefore, our next best option is to do the construction underground. So as a result, the underground is also nowadays getting heavily congested. As you can see in the picture on your right-hand side, we can see that there can be a lot of interactions between existing foundations, different tunnels, and so on. This is an area which has been studied quite well. However, most of these studies have been done in clay soil, which is mostly stiff clay soil. When looking at Sydney stratigraphy, it's mostly rock. As you can see in this typical section, we can find quite thin layers of residual soil and weathered rock, and then you can find competent shale and sandstone layers at shallow depths. Therefore, the tunnel interaction between in Sydney rock can be quite different to that predicted in clays. Also, in Sydney rock, there is very high lateral stresses that are locked inside the soil layers. The tunnel under our study or our interest was an existing utility tunnel which carries water at a high pressure. The pressure head inside the tunnel is about 60 meters head. There are 2 road tunnels proposed to construct crossing above these utility tunnels. The road tunnels are about 20 meters in width, and the clearance between this utility tunnel and the road tunnels is about 9 meters. So the tunnel itself has some added complexity. To start with, it has 3 liners. There are 2 concrete liners and there is a steel liner at the innermost. So near this inner steel liner, there is another hydraulic drain at the crown of the tunnel. The purpose of this hydraulic drain is to balance out any pressure differences due to the difference between the operational pressure inside the tunnel and the pressure outside the tunnel due to the groundwater elevation. So during our assessment, the key criteria that we were interested in was the deformations of the pipe, longitudinal bending moments, circumferential bending of the liner, and local buckling of this steel liner, radial cracking of the concrete liners, and also separation of these steel joints in this steel liner. To study this, we developed a finite element model in Abacus software. It was quite a large model with a 340 meter length, 150 meter width, and 120 meter depth. Coming into the results, on your left hand side, you can see the construction progress. If I run the video clip, you can see we are constructing the 2 tunnels progressively with a 20 meter lag between the 2. The actual utility tunnel is running underneath these 2 road tunnels. The right hand side clip shows the results. You can see here as these tunnels being constructed, you can see the utility tunnel, their deformations evolve progressively. As you can see, the highest deformation occurs at the crown of the utility tunnel, which is directly underneath the wider road tunnel. Having a closer look into the deformations, these red arrows show the direction as well as the magnitude of the deformations in the utility tunnel. As you can see, it pushes the tunnel face inside the excavation from the two sides. As a result, it pushes the crown and inwards more outwards and inward more outwards, so that the deformations at the tunnel ends up having an oval shape. Having a closer look into the horizontal stress regime, the leftmost figure shows the initial stress regime near the utility tunnel, the horizontal stresses. And once the tunnel has been excavated, as shown in the middle figure, the horizontal stress relaxes. Therefore, you can see at the sides, the horizontal stress has been reduced. As a result, the vertical stress, the horizontal stress at the invert and the crown has been increased. The stress regime near the utility tunnel did not change significantly due to the construction of the road tunnels. Looking into the stresses, these dotted lines show the initial stresses in the utility tunnel before the road tunnel construction has been done. So once the road tunnels are constructed, you can see the evolvement of these stresses. So the positive stresses means tension and negative stresses means compression. Here, what bothers us is the compression, because compression is the component that can cause any buckling in this steel liner. As you can see here, the stresses are, the magnitude is quite less. Therefore, it was assessed that this much of stress is not going to cause buckling in the steel liner. Looking into the longitudinal direction and the bending moments, again, this orange and yellow lines show the initial stress state, and the blue line and gray line shows the stress or bending moments after the road tunnel construction. As you can see, the bending moments have been significantly increased at the crown after the road tunnel construction. And this was something that we needed to have a closer look with a structural viewpoint. To summarize the results, as you can see in the table, the deformations, the maximum vertical deformation was only 4 millimeters, which is within the acceptable limits. And also the angular deformation or the gradient was within the acceptable limits. Thus, it shows us that the differential settlement will not be an issue. The stresses, hoop stresses and bending stresses were also within the acceptable limits. And the longitudinal displacements at the joints were only about 0.25 millimeters. That tells us that the joints are not going to open up and cause leakage. The change in ovality was only 0.05%, which gives us a measure on whether the concrete is going to crack or not. According to this result, the concrete will not crack in the radial direction. The only thing that caused an alarm was the local buckling, because the bending moments were quite high at the crown of the tunnel. So as a result, we seek the support from our structural group to have a closer look and assess the tunnel for local buckling. So that's the outcome of our study. Before I finish, I would like to acknowledge GHD for their help and encouragement to do more research, and also our geotechnical team, Kim Chan and Ashok Peiris, who are also the co-authors of this paper, and our structural team as well. Thank you all for listening.